Okay, and do you hear me better now? Okay. Well, first of all, I want to mention my collaborators before I run everything out of time. Lucila Juárez, Bernardo Mendoza, Guillermo Ortiz, José Samuel Pérez, Andrea López Reina, Raksha Singla, and well, I also want to thank Ed G, which collaborate with many improvements, contributions, suggestions, etc. Okay, so what is this program? It is a package to compute the optical properties, the electrical properties of metamaterials and on photonic crystals. It is in the public domain, so it is in GitHub, in CPAN, and it was programmed using the Perl language, the Perl data language, and the Mu object system. So first I have to talk a little bit about what is metamaterial. Um, minute. So these metamaterials are materials made from ordinary materials, from a mixture of particles of ordinary materials embedded in other materials, but that have properties that are usually or sometimes very different from the properties of the components themselves. So, for example, I show you here one of the first and quite famous metamaterials, which is the split ring resonators. So what I'm showing you here is this the electric boards that have a printed circuits and printed traces, metallic traces on it. And these traces have the shape of a circle of a ring, but the rings are interrupted. So when you have a magnetic field that is oscillating, that goes across these rings, it induces an electromagnetic an electromotive force that pushes the electrons around, but the rings are split. So then you have currents that are going around, but they cannot cross that gap in the ring, so they accumulate. So you get currents that are running around, and currents that run around produce magnetic dipoles. But then these currents are interrupted, so then you have charge accumulation, and this charge accumulation behaves like in a capacitor. So you have a kind of electronic circuit that has inductors and it has capacitors, and that has resonances. So it has an electromagnetic resonance at some given frequency that depends on the geometry. If you go a little bit above that resonance, then the permeability, the magnetic permeability of this artificial system can become negative. Also, maybe you can see that there are some traces that go in the back of these boards, traces also. So in the vertical direction, this system behaves as a conductor, and conductors have a negative permeability when you are at a low enough in the magnetic permeability, and they have a negative permittivity. So they can have a negative permittivity, negative permittivity. Sorry, I have to talk some physics to present my system. The index of refraction, the square of the index of refraction is given actually if any one of those is negative, the index of refraction becomes imaginary, and that means that electromagnetic waves of the system. But in this case, if epsilon is negative and mu is, if both are negative, their product is this number, and then the index of refraction is a real quantity, and then you can have propagation of electromagnetic waves, and they have a negative index of refraction. So let me try to explain to you what that means. This is the relation between the wave vector. No, here I cannot point at it. Okay. Well, the way the some given permittivity and permeability is proportional to the perimeter of the speed of light. If the permittivity is negative and the permeability is negative, the wave vector is real. That electromagnetic theory from Maxwell's equations for the electromagnetic field, it turns out that the electric field action of propagation of the phase of the wave vector, they form their right-hand rule. That means that if you move the fingers of your right hand from the electric field toward your thumb would point in the direction of the wave vector. Furthermore, the electric field, the magnetic field, and the propagation of the energy, the pointing vectors, right-handed orthogonal system. So if you go from the electric field to the magnetic field, your thumb points in the direction of the energy propagation. But if the permeability is negative, then the magnetic field is opposite to the the flux density, and that means that the energy propagation is opposite to the wave vector. So a wave that is moving in one direction where the phase planes are moving in one direction has an energy going in the opposite direction. And this is very strange. Let me show you why. Here I have a interface between an ordinary material and another yellow arrows represent the energy flux, the pointing vectors. So here you have an incoming wave that reaches an interface. Part of the wave is reflected and part of the wave is transmitted. But if the second material is one of these exotic materials, then the energy would go on the opposite direction. But in this case, the picture here cannot be real because if you shine light from the left towards the right on this interface, the energy in the transmitted wave, as I am showing it right now, is moving from right to left. That is wrong. The energy, if you illuminate an interface, the outgoing energy should go away from the interface. So you have to actually change the direction of the phase motion so that the energy moves away from the interface. But the phase is moving upwards in the incoming wave, so it has to move upwards in all of the involved waves. So then the energy is going downwards. So if the incoming energy goes upwards, the outgoing energy is moving downward. So this is refraction of light, but in an angle that is obeys Snell's law, but with a negative refraction. It is the opposite direction that one would expect in an ordinary. There are many others. For instance, there are metasurfaces. Here, what I'm showing is a surface in which small electric particles with these shapes, like a nail with a larger angle, or a D or a L with a smaller angle, are deposited on the index of refraction, so that the wavelength of light within these particles becomes very small and comparable to the size of the particles. Then you can have resonances of the type of the Me type resonances. And if light goes across these particles close to this resonance, the phase of light changes abruptly, changes by a large amount. But the precise frequency of the resonance depends on the shape of the particles. So if you modulate the shape of the particles as you move along the surface, you can also modulate the phase of an electromagnetic wave as it goes across this surface. And by modulating this phase, you can refract light in a non-ordinary way. You can refract light going beyond Snell's law of refraction. So, for instance, if light is coming into one of these materials, you can make it go straight on or refract downwards, depending on the polarization of the light. Or you can do metalenses in which you have arrays of this particle such that the phase is retarded a lot for the waves that go across the center of this metasurface, and it varies by a small amount for the wave that goes near the edge. And in that way, you can make a metalens. You can make a system that light that is going straight horizontally is bended downwards if it falls on the upward side of this metalens, or it is refracted upwards for light that shines on the lower part. So you get the same effect as in a lens, but a lens is a big piece, a wide piece of glass, and this can be nanometric in width. So you can make lenses that are very small and that can be used in integrated photoelectronic systems, optoelectronic systems. Finally, let me talk to you about photonic crystals. Imagine you have a transparent media where light can move along the transparent media. So this is how the dispersion of light looks like. As you increase the wave vector, the frequency increases. So the frequency as a function of the wave vector moves along these straight lines. But if this material is not homogeneous, but has some periodicity, for instance, you have actually two materials that alternate periodically, then you can have a diffraction of the light that is propagating in this system. And when it gets diffracted, it turns out that the wave vector can be changed by a quantity that depends on the period of the system, this distance d. So that means that this red line that is going here, the field that has, say, this wave vector and this frequency, becomes coupled to a field that has this other wave vector and the same frequency. So if you look precisely at this point, you can see that you have a crossing where light that is moving leftwards can be diffracted into light that is moving rightwards with the same frequency. So you have what is called degeneracy in physics. And anytime you have two degenerate states, this one going leftwards, but coupled to this one that is going rightward. If you have two degenerate states with the same frequency and they are coupled one to another, then the degeneracy is broken and you open up a gap. And this gap means that there is a region for frequencies where the electromagnetic energy cannot propagate. So this is what is called a photonic band gap. And the dispersion relation that describes how waves propagate within this kind of system look not unlike the dispersion relation of phonons in crystals or of electrons in electronic materials. So you have permitted regions and you have forbidden regions. Okay, you can take this to 2 dimensions or 3 dimensions, and you can make then metamaterials or photonic crystals that are able to trap light or to guide light. And if you have trapped light, then and have an atom that has some electronic transitions, you may suppress those transitions if the light cannot go far away because light comes back and excites the electron back to the original state. So you have a virtual particle. So there's many physics that is related to this kind of photonic crystals. So what I want to talk to you about is how to calculate the properties of these systems. So the optical properties of these materials depends on the composition of the materials. They are metallic or the electrics in the conductor, whatever. But it also depends on the geometry, depends on the size of the particles. If you have an arrangement of particles within a host, depends on the size, depends on the shape. So the question is how to calculate them. And one of the many ways one may proceed is through an effective response, changing this system that has a texture, but a system that is completely homogeneous, but that has effective properties. And the problem is how to calculate those effective properties of this effective homogeneous material that has the same optical properties as the original material. So I'll show you some of the theory. So the electric properties of a material are described by the electric function, which is defined here. The displacement field is given by the electric response multiplied by the electric field. So what we want is the macroscopic response. So we want to get the macroscopic displacement field, which is some kind of average of the microscopic displacement field. And we want to write that as a macroscopic permittivity multiplied by the macroscopic electric field. However, as the electric field fluctuates as you move around in the original system, the electric field changes when you go, say, from the green region to the blue region, then the product, the average of the product is not the same as the product of the averages. That means that therefore, the average of the dielectric function is a quantity that has no clear meaning. I state here that it is actually meaningless. So what we have to do is to find some operator whose average does have a well-defined meaning. So I'll show you an example of how one can proceed. The example is based in materials that have a very small scale, much smaller than the wavelength of light, so that one can ignore what is called retardation, the time that takes for light to go from one part of the material to another part of the material, from one unit cell to another unit cell, or to go across a particle. And we'll pay attention to the longitudinal response. So maybe you know that any vector field can be separated in two parts, a longitudinal projection and a transverse projection. So what I want to look now is at the longitudinal projection of the displacement field. The definition of a longitudinal field is that its curl is equal to 0. So the curl of the longitudinal part of the displacement field is 0 by definition. And the divergence of the longitudinal part of the displacement field is just the external charge. That is what Maxwell's equations teach us. So it turns out that the longitudinal part of the displacement, not the full displacement, but only its longitudinal part, obeys the same equations as the external electric field, because in the non-retarded limit, the external field is a longitudinal field, and its divergence is the charge, which if you just look at the external field, that is the external charge. So then we can identify the longitudinal projection of the displacement as an external field that is unrelated to the material. It has nothing to do with the material, so therefore it has no spatial fluctuations induced by the texture of the materials. That means that if you invert the equation that relates D to E and write the electric field as a response function, which is the inverse of the longitudinal projection of the permittivity, acting on the displacement field, if you first invert, then you can average. And since D has no fluctuations, then the average of this product, in this case, is just the average of the products. But the average electric field is a macroscopic electric field, and the average displacement field is the average longitudinal. I forgot here to put an L. Ah, no, there it is. The average longitudinal field is just the macroscopic displacement field. Therefore, one can identify the response function here in the middle with the macroscopic response. So we have a recipe here to calculate the macroscopic response of the system. The response to an external excitation is simply the average of the microscopic response. So let me show you how to apply this in a binary system. That is a system that only has two materials. So the permittivity, what I call the microscopic permittivity, has two values, either epsilon b, for instance, when we are in these green regions, or epsilon a, when we are in these red regions labeled A and B. We can define or characterize the geometry of this system by a characteristic function that takes two values. One, when we are in the inclusion, when we are in the green regions, and 0 when we are in the host. So this takes care of the geometry. And this dielectric response then can be written in terms of this characteristic function simply as some number epsilon AB, which is given by the difference in permittivities, multiplied by U minus B, where U is what is called a spectral variable, is something that depends on the composition and the frequency, depends on the electric function of each of the materials, and B, which is this function that depends exclusively on the geometry, okay? So we want the macroscopic response. I'll introduce a periodic system. I'll assume that the system is periodic. So therefore, it has a Bravais lattice, a lattice of vectors such that if you move by any of those vectors, if you take, for instance, a step to the right or a step to the top in the vertical direction, or two steps, one after the other, you end up in a position that is equivalent to the original position. So that defines this R lattice, R vectors. And you have a reciprocal lattice, which are those wave vectors corresponding to waves that don't change the phase when you go to one site to an equivalent site. So one can describe a crystal in terms of this reciprocal lattice. Then the longitudinal projection of the electric response turns out to be just the Fourier transform of the dielectric response multiplied by unit vectors on the right and on the left. These are unit vectors in the directions of vectors of the reciprocal lattice. So this is like a matrix representation of the dielectric response, where the indices are the reciprocal lattice vectors. And I have to take the inverse of this matrix, so I have to take the inverse of this large matrix, which it turns out that can be written in terms of the inverse of U minus the longitudinal projection of B, where B is the characteristic function. It turns out that this is a Hermitian operator. So this equation looks similar to what you get in quantum mechanics, where one calculates Green's functions as the inverse of some complex quantity, some complex generalization of the energy, minus the Hamiltonian, which is the energy operator, which is a Hermitian operator. Hermitian in the sense of linear algebra. So to take the macroscopic response, the inverse of the macroscopic response is the 0, 0 component, because taking the average is the same as taking the reciprocal vector equals to 0. That means taking fields that oscillate very slowly in space. So it is like projecting into the 0 state of the inverse of U, complex constant, complex number, minus B, LL, which is a Hermitian operator. And that looks like the projected Green's function in quantum mechanics. I'm sure, I guess many are not following, but what I want to emphasize is that one can borrow methods that were developed for the calculation of this kind of stuff in quantum mechanics and apply them to electromagnetic calculations. So what we implemented was a Haydock recursion to calculate the macroscopic response. The idea of Haydock's recursion is the following. You have an operator, say H. You have a starting state. In this case, we take the macroscopic state, which is simply a plane wave with a very small wave vector. And then we apply H on state 0 to produce a new state 1. Then we apply H to the state 1 and produce a state 2, and we do that iteratively. But each state produce, which is the state, we orthogonalize it to all the previous states we have already found. And since the operator is Hermitian, we actually just have to orthogonalize it to the last two states we have had. So in that way, by demanding that the new state is orthogonal to the previous states, we are constructing an orthogonal basis in which the operator can be represented as a three-diagonal matrix. And this is the recipe for obtaining these elements A and B that appear here, A and B. And the matrix is a three-diagonal matrix which has lots of zeros, except on the main diagonal, where it has these A coefficients, and above and below the diagonal. Sorry, this -1 should have been a subscript. That mistake. But the diagonal above and below the main diagonal is given by these B coefficients. So what we have to do is to apply the Hamiltonian to the states recursively. In our case, the Hamiltonian is just the longitudinal projection of the characteristic function, and this is the Fourier transform of the characteristic function multiplied by the unit wave vectors in the direction of the reciprocal wave vector. So how can we apply this? Well, if we have a given state, call it n, we can represent it by a wave function in reciprocal space, psi of n. This is just the Fourier transform of a wave function in real space, psi of r. So once we have the wave function in reciprocal space, we simply multiply it by g, by this reciprocal wave vector, unit reciprocal wave vector, and then we have to multiply it by b of g minus g prime and add overall values of g prime, but that is a convolution. So if I take a Fourier transform into real space, that is just a multiplication by b of r, and b of r is just a number, 1 or 0, depending on if I am in a particle or within a hole. And then whatever comes out of that, I transform it back to reciprocal space and multiply it by this last g. And therefore, I can obtain all of the coefficients A and B without making any matrix multiplication. Okay, so this is the summary of the theory of our theory. We have microscopic operators. Microscopic operators, we are looking for a macroscopic operator whose inverse is just the average of the inverse of this microscopic operator. We have, for example, the macroscopic dielectric function is given by the inverse of u minus the longitudinal projection of the characteristic function. We construct a basis in which our operator is three-diagonal. We construct this basis using Haydock's recursion. We initialize the recursion using the macroscopic state. Therefore, we get a three-diagonal matrix. And finally, we have to invert that matrix and project it into the macroscopic state. But that is just one element, the element 0, 0 of the whole matrix. And it turns out that for three-diagonal matrices, we even have a formula for that element of the inverse. So we have a continued fraction representation for the macroscopic dielectric function. And just emphasize that all the coefficients A and B depend on the geometry. U depends on the composition. So we can, for one geometry, we can compute the Haydock coefficients and then use that geometry for different compositions, for different frequencies, and make many computations of the response. And this works with dissipation or without dissipation, with dispersion or without dispersion. So it is useful for the electric and for metals. So let me give you an example of how this works. I hope the example works. So first, one has to make um, one has to define the characteristic function. So now I'm using PDL, the Perl data language, and I will construct a small characteristic function. So I use this function zeros with some given number n small, which I took as 21. So this line here gives me an array of 21 times 21 zeros. Then I apply the method rvals that gives me the set of distances from each point in this array to the center of the array. And I compare that number with a given desired radius, in this case, 35% of the size of my square unit cell. So this will give you, I'll just run this code and see what happens. Okay, so what you see here is an array of zeros and ones. So this is the characteristic function. It's a very small characteristic function that somewhat resembles a circle. It's like a low resolution circle, right? One can use more complex functions. For example, here I use the arc tangent of some angle that is related to the x coordinate and the y coordinates for the same array. And if I run this small code fragment here, then I produced something that looks like a square, like a cross, sorry, a cross instead of a circle. So the idea is one can generate simple shapes, and then one can generate complex shapes using the union or the intersection of simple shapes. And one can use the bitwise disjunction and conjunction operators to perform this union and intersection and obtain complex shapes, whatever shape one is interested in. So what I'll do here is to generate another, again, a circle, but with a more resolution, with a higher resolution. And then I'll just display the results. So you see here you have the circle with a better resolution. You have this kind of jagged edge. This is a 201 times 201 array. So it looks much better than the previous one. Now what I'll do here is I use a function, an utility function, which I call tile, just to make several copies of the unit cell, because I'm yeah. Okay, so here you see the array I am considering. So this is an array. It's a part of an infinite array of circles. You can look at this as cross sections of a system made of cylinders. Okay. So to use my system, once you have the geometry, I have a class that produces a geometry object from a characteristic function. So what I do here is I initialize that object, telling it what is the characteristic function, what is the direction of the wave I want. So in this case, I will take a wave that is moving in the 1, 0 direction. That means the x direction. And what is the size of the unit cell? So I took a unit cell that is normalized, that has a size of 1 in the x direction and the y direction. So I run this code. There is nothing to show for the results. And this is just something I will use later on. So now I have the geometry object. I can use the geometry object to find information about my geometry. So for instance, from the geometry, I can get R. R is just the lattice positions, the positions of all the pixelated points in my array. In this case, they are pixels because I used a 2-dimensional array. I could have used a 1-dimensional or a 3-dimensional array to initialize my geometry. So I take a slice of this of this array, and I format it, and I'll just display some points within my array. I can, here I'm taking a slice on the opposite side of the array just to see how it looks. I can look at the reciprocal lattice. I can get information about the reciprocal lattice, or can get the reciprocal lattice itself from one extreme or the other extreme of the array. And I can get the magnitude of these vectors, and I can get the normalized vectors and their magnitudes, which should be 1. So let me run this code, and the results are here. The filling fraction is about 1/8. That's correct, because in this case, my radius was 0.2, 20% of the unit cell. So this is the area of a circle of radius 0.2. So it's for this 1 to 5. The real, yeah. Oh, yeah. Okay, thank you. Okay, so I was telling you here are some values of these arrays. So it starts at 0, 0, and it is growing by 0.005, by 0.005 in the x direction and in the y direction. If I go to the other extreme of the array, then it goes up to 995. The reciprocal lattice is the scale reciprocal lattice starts in 0. If I go to the opposite side, it has negative numbers. This has to do with the fast Fourier transform and the way conventional way it uses the wave vectors. Okay, so this is the normalized reciprocal lattice, and the magnitudes, of course, are 1. So once I have a geometry, I can use that geometry to initialize an object that computes a Haydock coefficients. So here I just use the geometry and the number of Haydock coefficients, the maximum and number of Haydock coefficients I want to use. And then with once I have a Haydock coefficient calculator, I can use it to calculate the electric function of the system, macroscopic the electric function, projected into the given the direction I chose when I made up the geometry. So I initialize the epsilon, the electric function calculator, with the Haydock calculator, with the number of desired Haydock coefficients, with the electric function of the host, which in this case I took vacuum, the electric function of the system, which in this case I took glass, epsilon equals 2, and I just print the macroscopic response. Takes a little time to calculate the Haydock coefficients, but it is done. The electric function is 109, and I use here an analytical formula to estimate the electric function, and I get exactly the same result, which is not surprising because this is a formula that holds for systems with for a circular lattice with a small filling fraction. So this is not very interesting, but at least it shows that the result is correct. So what I'll do now is make calculations for a metal. So first I make a function to calculate the response of a metal using the Drude model. And then here I'm just plotting how the response of a metal looks like. So the response of a metal is negative for frequencies lower than the plasma frequency, and then it becomes positive. And now what I do is I use this Drude response as the value of the epsilon of the particles, and I do an array then of the electric function calculators, I get the actual value of the macroscopic response for each of them, and I put them, save them in one array, epsilon of the wire, and then I plot them. This is what I do with this code up here. Okay. And the result is here. So here we have the spectrum, the macroscopic permittivity as a function of frequency, which this is the imaginary part. That means that the system has no absorption of light except at this resonance. And the numerical calculation and the Maxwell-Garnett calculation, the approximate analytical calculation, they both agree quite well in the position of the resonance. Agree because the filling fraction is very small. Now I do the same, but for a larger filling fraction, just by taking the radius of my system. I take a system with a larger radius, and the code is basically the same. So wait a few seconds. Okay, and the results are here. So this is the array of fat particles, and this is the response. We still have this dipolar response, but the Maxwell-Garnett theory no longer agrees with the numerical. The numerical result is further shifted towards the red end of the spectrum, and it has additional resonances, and these resonances have to do with multipolar resonances. I can change the aspect ratio of the system by stretching the lattice parameter along one direction, which I do with this, the lattice parameter. I introduce this number 2 here. So let me run this code. Took a little bit longer. It takes about twice what it took the previous way, because now I'm calculating the response along 2 directions, as the system is no longer isotropic. So now the system is this, it's elongated in the vertical direction, and I have 2 response functions, one along the x-x direction, one along the y-y direction, and I'm plotting here also the response for a square system. So you see that there are some resonances that coincide with the square, and some resonances that don't coincide with those of the square. Now, I didn't mention it, but once one has the tridiagonal response of the system, one can calculate not only the macroscopic response, one can actually calculate the microscopic field. So there is an object to calculate the fields. So here it is, a field calculator, which is initialized with a Haydock calculator, as we did some minutes ago. So this will take some time. Okay. And now I can show you the fields in 2 of the resonances of the previous plot. So you hear this one. So at the frequency here, above 0.3 and something, you see a resonance, you see these hotspots where the field is very large. And this looks like a dipolar resonance where the field within the particle points basically along one direction from right to left. And here I have another resonance, and this is kind of a hexapolar resonance where the field lines goes from this hotspot to this one, or from this hotspot towards this one, in this direction and in this direction. So one can do other things. For instance, I can manipulate, I can include the specific directions of the primitive vectors so that I can shear the structure. So here I'm going to share the structure. Just for the shared structure, there is there are no known. I don't know why this. Some mistake. Something outage. It did finish. Okay, once one has the shear system, I hope it doesn't take too long, but now my time is almost running. Hopefully in a few seconds, we'll have, I can show you the results. Okay, there it is. So this is the system I'm calculating now. And then the system, I have to calculate the full tensor. So that's why it took longer. I have to calculate the XX, the XY, and the YY components. I compare them with those of the square. And I can also get the fields, but I think I should run now. So let me get back to the presentation. So what I hope I could show you is that the calculation of the full spectra takes as long as the calculation of a single point. The 2D binary cases, they are running in a few seconds in this laptop that I'm using that's quite old. The programs can be easily parallelizable and can be used to tune resonance frequencies, the transmission and absorption spectra, polarization, whatever. And they allow the design of photonic devices by optimizing the geometric parameters. The system was built using the move object system. The idea is to join pieces to make different programs. The pieces would be the geometry, the Haydock calculators, the dielectric tensors, or the field calculator, or the Green's functions calculator. The geometry, for instance, can be obtained from the characteristic function, but it can also be obtained from an actual image, a two-dimensional pixelated image, or from a dielectric function or from a dielectric tensor. So I have several classes that obtain the geometry from the characteristic function or from an image, from the dielectric function, etc. But they all consume a role, the photonic roles geometry, and that way I avoid repeating the codes. Similarly, the Haydock coefficients can be obtained for the longitudinal, the electric field in the non-retarded case, or from the wave equation using a spinor representation. And there are many ways of calculating it. So there is a Haydock rule that avoids repeating codes for all the different situations. And I'll just give you one example, one more example and finish, which is this kind of beetles, which have iridescent metallic reflections. And it turns out that the cuticle of these systems is given by a layered structure, and each layer is composed of fibers that have a slightly different orientation as one moves upwards. So this is a kind of a naturally occurring photonic crystal because it repeats itself periodically after the fibers have made one half turn. It is chiral. It has many layers. Each layer has a different tensorial dielectric response. So it's actually the same, but it is rotated. So from one of these responses, one can get all the other ones by rotating. So what I'm showing now is the Green's function obtained with the photonic package for this system, projected into a polarization state. This is a retarded calculation. corresponding to light that is propagating and rotating in a given direction. What I want to show you is that this line is intense at those frequencies and wave vectors that correspond to a normal mode that can propagate within the system. So you can propagate for these frequencies here up to this region. When there is a gap, there is a forbidden gap. That means that circularly polarized light, it cannot propagate into this system in this frequency range. And light with the opposite polarization would not be able to propagate backwards in this frequency range. So the idea is that this explains why light cannot penetrate these kind of systems when it has a given circular polarization. So has to be reflected. If cannot be transmitted, is reflected. And here is the result of an analytical theory, exact theory for the same system. And you see that it agrees perfectly with the numerical calculation. So I leave you with the conclusions. We implemented a recursive procedures based on a Haydock representation. We translated Maxwell's equation into Hermitian or symmetric operators that can be represented as three diagonal matrices. We obtained a macroscopic response. From that, we obtained the photonic bands. We obtained the microscopic fields. We can apply these to metamaterials with arbitrary composition and geometry. They can be dielectric for metals, dispersive, dissipative, isotropic, or anisotropic. It was implemented in open free computational package photonic, and it uses Perl, taking advantage of its expressivity and flexibility. And we used Mu objects, and the Perl data language for efficient number crunching. And I leave there an example of the use of the package. And thank you very much for your attention.
Thank you, Dr. Mochán. Okay, I have one question before we start. John Napierkowski's talk, I have one question for Dr. Mochán. After listening to all of that very amazing math explanation that you have for all of us, I'm wondering from a layman's point of view, or at least someone that does not understand all of the physics yet, I'm working on it. What are some of the futuristic things that could appear sometime in the future, like transparent aluminum or light bending cloaking devices or radio antennas that can pick up something from Mars, but they're microscopic in size? What kind of things could you do? Just make up some amazing futuristic inventions, Ornan.
Okay, there are many examples that are quite amazing. One that became very fashionable is that one can make materials that bend light around obstacles so that you cannot see at whatever is hidden within the obstacles. But then the light gets out and propagates as if it was never, as if it had been propagating on a straight line. So that cannot be fabricated with ordinary materials, or it can be fabricated with metamaterials. There are things that are interesting, for instance, in the spectral response of the metamaterials. One can, for example, tune metamaterials so that they have a strong absorption band in that region of the spectrum, of the electromagnetic spectrum, where the atmosphere is transparent. That way, if you put one of these materials, if you take it outside, it can radiate light and lose light to the exterior space without interacting with the hot atmosphere. So that way you can get the surfaces that cool even when they are in the sunlight. If they don't absorb sunlight, but emit very efficiently in that region where the atmosphere is transparent, then they can cool because they interchange energy with the space. Um, with Merlin, we have been working on adapting different geometries in order to make accelerators in the very small scale, in centimeter scale, particle accelerators. So I don't know, there are many things, and one can start fantasizing also. But I hope I answered well. Yeah.
Thank you, Dr. Mochán. That definitely helps answer my question, and I hope that we can all think of some other new, fascinating, interesting ways that we may be able to use metamaterials and get Perl ready to help us with that. So I think we're ready for our next person.